Hello and welcome back. It's time to talk about what happens when the law of sines gets complicated, and that is what we call the ambiguous case. It comes about whenever you're dealing with a side-side angle scenario. If you have difficulty remembering that this particular scenario can be complicated, just remember that this situation is the one that creates sort of a pain, and if you look carefully at the letters, you might figure out a way that you could remember which situation particularly is the pain when you're dealing with law of sines. So if we're dealing with law of sines, the ambiguous case, we've got angle B, side C, and side B. And we don't know anything about this triangle aside from the fact that we know angle B, side C, and side B. So the first scenario that occurs when side B happens to be a little bit too short. And if side B is too short to create a triangle, it would just sort of dangle here no matter what. It's just not long enough to create a triangle. I don't know how long this side is, and I don't really care how long this side is. This would be side A. Because if this thing is too short, I'm not going to be able to complete this triangle no matter what, whether it's coming down here or coming over this way. It's not completing a triangle. So if this side ends up being too short, I can have situations where I try to use the law of sines and I don't get any triangle as a solution. You might get something that looks like this if you get like sine of theta equals 1.2. Well, sine can't equal 1.2. That'll tell you that there's no solution. The second thing that can happen in this particular scenario that is ambiguous is what happens if, when this thing dangles back and forth, there's only one triangle that's completed. Well, if there's only one triangle that's completed, that would mean that when I drop this line, there's only one spot where it would touch this line A. Well, if there's only one spot, then it couldn't be a situation where there's two spots. And if that's the case, then this thing has to be going straight downward, which means that this has to be a right angle, which means that in this particular situation, we're going to end up with a right triangle. And that's our second sort of situation when we're dealing with this scenario. Now, I should note that these are all dealing with scenarios where angle B is acute. If angle B is obtuse, then we can get some more stuff going on. But this situation is the one that really gets complicated. This is the ambiguous situation. So we've got angle B, we've got side C, and we've got this side, and it could be that this side comes down this way, or if I were to kick it out, this side could also come down this way. And so there are actually two different ways that we could complete a triangle in this particular scenario. And that can be really, really problematic if we're trying to get only one solution. If we know that we can have multiple solutions, then we just write down that there are multiple solutions and we find out what both of them are. So I'm going to walk you through a few different scenarios dealing with law of sines and how we look for whether or not we have to worry about the ambiguous case. So let's start off with a situation where, sorry, let me move some stuff around here. Let's start off with a situation where we have triangle QRS with side Q having a measure of 15 units of some sort, side R having a side length of 28, and Q having a measure of 43.6 degrees. In this situation, we have an angle opposite a side, and we have this thing, which we're going to call R, which means that we can use that to find out what this angle R is. So we would set up that the sine of 43.5 degrees divided by 15 is equal to the sine of R divided by 28. Pretty straightforward right now. Now, if I go through and multiply this side by 28, and I try to evaluate or solve this thing, I'm going to end up with something that says 1.287 is equal to the sine of r. Well, 1.287 can't equal the sine of r because sine is always restricted to being values between -1 and 1. So if I get something that looks like this, that tells me that there is no solution. So this triangle does not exist, and I can say no solution and be done with the problem. We like it when that happens. That makes our life pretty easy. Let's look at some situations where our life is not quite as easy. So let's say that we have triangle XYZ. We know that x is equal to 23.5, y is equal to 9.8, and angle x is equal to 39.7 degrees. So if we're setting this up, we could say that the sine of 39.7 degrees over 23.5 is equal to, this was y, which means that this will be uppercase y. This would be the sine of y divided by 9.8. And if we go through to try to solve this thing, sorry about that, we'll end up getting something that says that the sine of y is equal to 0.2664. Now that I like seeing because sine of y is able to equal 0.2664. And if you think about it in terms of a triangle, there are actually two angles where the sine of y would equal 0.2664. If you recall from the unit circle, if this is at 1 and this is at 0.5, 0.2664 is about here-ish. Well, if we're coming through on our unit circle, we're interested sort of in this angle right here. But the unit circle keeps on going around. It comes down this way also. And there's also a value here. And this is a value that can be found in a triangle because that's going to be less than 180 degrees, which means that it's a conceivable angle measure for angle y. So let's see what happens when we do this. If we take the inverse sine of y, we end up getting that y is about 15.4 degrees. Well, if that's 15.4 degrees, that means that this right here is 15.4 degrees, which means that this thing, this big angle right here, would be equal to 164.6 degrees. Now, what that means is that we need to know whether or not we need to care about 164.6 degrees as a solution. And we can't have 164.6 degrees as a solution, mainly because of this number right here. If I've already said that one angle is 39.7 degrees, and I make another angle be 164.6 degrees, then I'm well over 180 degrees already, which means that this angle is an impossible angle within the triangle, which means that there's only one angle that I need to care about, and that angle is 15.4 degrees, which means that that's the only angle measure that I'm going to care about as my angle y. Once I know what x is and what y is, I can use the fact that my angles have to add up to 180 degrees to find out what angle z is. And angle z is going to be equal to 124.9 degrees. I can then use the law of sines again, and you could go through and do that on your own. We'd still set it up with sine of 39.7 over 23.5 equals, this time it'd be the sine of 124.9 over z. And if we solve that, we'd find that z, little z, is equal to about 30.2 units. So we have solved our triangle. We had x, y, and big X, the angle, and now we have our other two angles as well as our other side. And that solves our triangle. Now let's look at a situation where we actually end up with two different triangles as a solution. So let's look at angle ABC, triangle ABC, where B is equal to 15, C is equal to 20, and B is equal to 29 degrees. If this is B, then this is side B, so B, and this is side C, which means that this is angle C. So we could say that the sine of 29 degrees divided by 15 has to be equal to the sine of angle C divided by 20, because those are my opposite angles with opposite sides. This shouldn't be too difficult for people to go through and solve. I'd end up with sine of C equaling about, sorry, let's make that into an about sign, 0.6464. Now, going back to our unit circle again, if sine has to be about 0.6464, then within my circle, 0.64 is around here. Well, there are, once again, two different angles that make this happen. One of those angles is going to be equal to 40 degrees, about. So this angle right here is equal to 40 degrees, which means that this angle right here would be equal to 180 minus 40, which is 140 degrees. And this time, both of those angles are possible, because if I make C be equal to 40 degrees, then these add up to 69 degrees, which means that angle A is going to be equal to 111 degrees, because the three angles would have to add up to 180. If I make angle C be equal to 140 degrees, then with B still equaling 29 degrees, that would add up to 169 degrees, which means that my missing angle would be just 11 degrees. And I don't know which of these triangles is my answer, which means that for right now, both of these triangles are my answer. I have 40 degrees and 111, and I have 140 degrees and 11. And notice that both of those add up to 151 degrees, which is the supplement to 29 degrees. So now that I know what my possible angles C and A are, I can use those to find out what my last value, which is going to be little a, is. So I could set up the law of sines. Sine of 29 degrees over 15 is equal to the sine of 111 degrees. Oops, let's get another one in there. Over A. And I could set up that the sine of 29 over 15 is equal to the sine of 11 degrees over A. You should have the skills necessary to solve each of those at this point. And if you went through and solved the first one, we would end up getting that A is equal to 29. And if you went through and solved the second one, you'd get that A is equal to 6. That means that we actually have two different triangles that can come about from this set of information, B, C, and angle B, which is why this is called the ambiguous case. There are actually, I think it's 8 different ways that the side-side angle situation could potentially play out. And personally, I don't think that it's really worth memorizing what's going to happen in each of them. I'd prefer to say, first of all, if the angle that you know is obtuse, then you don't have to worry about a second angle or a second set of solutions. But if it's acute, I'd just do a quick check. It's not that difficult to check whether or not this secondary angle is viable or not. And if it works, then find that second set of solutions. If it doesn't work, then you don't need to find the second set of solutions. And you can keep it simple. So hopefully that was helpful for people, and they can see how to use the law of sines with the ambiguous situation. Hope everybody's okay, and I'll talk to you guys more soon. Bye.